The intent of this video is to review the results of a World War II study comparing the structural performance of Japanese aircraft aluminum with U.S. aircraft aluminum. During 1943, the U.S. captured 3 Japanese aircraft. Components of the aircraft were sent back to the U.S. for evaluation. The evaluation included specifying the chemical composition of the aircraft alloy and performing static tests to ascertain the mechanical allowables. The composition and tested values could then be compared with U.S. equivalent material allowables. Information on the 3 Japanese aircraft evaluated are shown on this page from a declassified January 1945 Technical Air Intelligence Center Naval Air Station document titled Metallurgical Exam of Japanese Aircraft Sections. The aircraft code names Dinah, Judy, and Lily are shaded. The Allies adopted code names for the Japanese models. The Japanese equivalent model type and symbols are listed in this column. The Judy's wing arrived at the test house crated, as shown on this view. The wing was sectioned into various subcomponents for coupon extraction. This table lists the aircraft components extracted. The columns are the part identifier number, aircraft and part name, and weight of component in grams. The chemical composition of the aluminum parts evaluated are listed in this table. The columns are the part number, aircraft, chemical composition of the aluminum alloy, and similar U.S. alloy equivalent. There are 3 U.S. equivalent alloys identified. The U.S. aluminum alloy 24S has a chemical composition equivalent to the modern-day ASTM 2024 alloy, and it is used in today's airframes. The alloy 17S has a chemical composition equivalent to the modern-day ASTM 2017 alloy and is used in modern-day rivets. The alloy X76S has a chemical composition equivalent to the modern-day ASTM 7076 alloy, but it is not used as a modern-day aluminum alloy. Copper is a dominating alloy element for all the parts except for the Judy's wings front spar, as shaded in this row. The dominating alloying element for this part is zinc. A rule of thumb for modern-day airframes is to adopt copper-based aluminum alloys for their superior fatigue, crack growth, and corrosion resistance, whereas zinc-based aluminum alloys are selected for static strength and parts loaded in compression. For example, a commercial airliner's lower wing skin will be copper-based aluminum due to its cyclic tension loading, whereas the upper skin will be zinc-based aluminum, which provides better performance to the span-wise compression loading. The laboratory will need to cut coupons from the components collected for destructive testing. The coupons will be static tested to measure various material allowables for comparison with U.S. allowables. The test coupons will need to be machined from sectioned parts, like this wing rib. The specimens will look like this dog bone or round bar coupons. The coupons will be statically tested to failure, and the load and strain will be measured while in the test. The load and strain will be converted and plotted into a stress-strain curve, like this image from a 1998 Department of Defense document titled Metallic Materials and Elements for Aerospace Vehicle Structures. The x-axis is a strain, measured in inches per inch. The y-axis is a tensile strength measured in KSI. The key test result parameters are shown on this page. The ultimate tensile strength is a measure of how much stress the material can sustain to failure. The yield strength indicates how much stress the material can sustain without plastic deformation. The elongation is a measure of the deformation to failure. This is a measure of the material's ductility. Ductility is a very desirable property in aircraft structures. This table lists the results of the Japanese part coupon testing. The columns list the aircraft and part number, product form, thickness of coupon, alclad layer if applicable. Aluminum is identified as alclad if the aluminum sheet or plate alloy has a thin layer of pure aluminum roll bonded onto the stronger inner core. The thin layer of pure aluminum increases the corrosion resistance of the stronger core aluminum. You can tell an alclad finish by the mirror-like appearance, like the outer skin of this B29. Non-clad aluminum will be about 10% stronger than an alclad alloy and can be identified by having a dull finish, like these B29 fuselage center section skin panels. The remaining columns identify the similar U.S. aluminum alloy equivalent, hardness, tensile strength, yield strength, percent elongation or ductility, and the number of coupons tested. This page provides a summary of the findings. Microstructure and hardness indicate the alloys were heat-treated and naturally aged, no strain hardening. Tensile allowables were slightly lower than the U.S. equivalent. The alclad layer was of high quality with good diffusion, which suggests the proper solution heat treating and naturally aging steps were followed. An anodizing layer was observed on the rivets and tubing. Anodizing reduces a part's susceptibility to corrosion. This chart lists the U.S. aluminum alloy structural allowables from a November 1943 B-29 bomber structural repair manual. The significant columns of the table include aluminum alloy code, product form, thickness of finished part, and minimum tensile strength. These charts list the modern-day 2024 allowables in the -T42 temper, bare, and alclad, which would match the 24ST naturally aged heat treat temper. There are no modern allowable tables for the 2017 or 7076 alloys. Based on the data provided, we can roll up the allowables into a single table for evaluation. These rows have insufficient data for evaluation, so they've been removed from the database. This table lists the Japanese aircraft part and number, product form, alclad layer or not, and thickness. The last four columns are the tensile strength of the part tested, the 1943 B-29 equivalent allowable, and the modern-day tensile strength values for comparison. The tested Japanese part strength exceeded both the 1943 and modern-day allowable, except for this Dyna flat fitting row shaded. Overall, the Japanese part had 11% higher tensile strength than the U.S. similar aluminum alloy. Although the report indicated the Japanese strength allowables were slightly less than U.S. period allowables, the comparison conducted showed the opposite. The discrepancy in strength levels may be due to the low sample size or the aluminum alloy not exactly matching the U.S. alloy in composition or heat treat temper specification. The B-29 allowable data was defined as a minimum allowable, and the modern-day ASTM allowables were extracted from a B basis confidence and reliability and 95-95 respectively. If you found this video of some value or have any additional information to add, please comment.